And we're live.
Hello, and welcome to our keynote today by Erin LeDell on responsible automation towards interpretable and fair AutoML. My name is Sadiqa Watson, a data science consultant at Corelasi Data Insights. If you're watching this live, you can ask questions on Slido. The link is in the video description on YouTube. Before we begin, I'd like to send a special thanks to the useR conference organizers for putting together such an amazing virtual program. I would also like to thank RStudio for their sponsorship and support of the useR conference. Now, I'd like to introduce our amazing speaker for today's keynote. Erin LeDell is the Chief Machine Learning Scientist at H2O.ai, the company that produces the open source distributed machine learning platform H2O. At H2O.ai, she leads the H2O AutoML project, and her current research focus is automated machine learning. She is the maintainer of the H2O R package and the co-author of a handful of other R packages. Before joining H2O.ai, she was the principal data scientist at Wise.io and Marvin Mobile Security, the founder of Data Scientific Inc., and a software engineer at a large consulting firm. She is also founder of the Women in Machine Learning and Data Science organization and co-founder of Our Ladies Global. Erin received her PhD in biostatistics with a designated emphasis in computational science and engineering from University of California, Berkeley, and has a BS and MA in mathematics. And with that, I will turn it over to Erin for her keynote on responsible automation towards interpretable and fair AutoML. Let's welcome Erin to the platform.
Thanks, Sadiqa. Okay, I'm going to go ahead and share my screen. Okay. Let's see if that's working. Okay. Looks like it's working on my end, so I'll just go ahead. So I wanted to thank the conference organizers for inviting me today. It's really a great honor to be a keynote speaker at useR. My first useR was in 2014 at UCLA, and I've been coming to useR ever since. The only one that I didn't go to was the Australia conference, which was too bad that I missed that one. So this is really my favorite community and my favorite conference, so I'm really happy to be here. Today I'm going to give a talk about automatic machine learning, and this is a topic that I've been working on for the past 4 years. And today I'm shifting the focus away a little bit from my usual talk, and I'm going to focus more on what's something I think is really important, which is the responsible use and development of AutoML tools. So the agenda for the talk includes first an introduction to automatic machine learning, or AutoML, along with the H2O AutoML algorithm, which is a function included in the H2O package. And then next we're going to talk about what interpretable machine learning is and what it's good for. And then I'm going to introduce a concept called algorithmic fairness, and that has to do with protecting marginalized subgroups when you use machine learning. And from there, we're going to talk about when it's actually not appropriate to use machine learning to solve a task, and how do you go about making that decision. And then lastly, I'd like to talk about what I think is next for machine learning from a theory and methods perspective with respect to these topics. And the link below is a GitHub repo, which has my slides, and we'll also have some R code in there for a demo that I'll review later. Okay, so first, just automatic machine learning. So what are some of the goals and features of AutoML? So I think one of the main goals is to, or maybe the most obvious goal is to, given a data set, train the best model that you can in the least amount of time. And then another goal, which I think is also a feature, is that we can reduce the amount of human effort and expertise required to be an effective data scientist with AutoML tools. And one of the nice features of AutoML in general is that the performance of the models produced by an AutoML system is likely better than what your average data scientist could produce by hand. It's not uncommon that an expert data scientist can engineer a better model than an AutoML tool, but overall, these tools give a pretty good and at least starting point for a given data set. And then lastly, I think one other nice feature about AutoML is that these tools can quickly establish a strong and reproducible baseline for any new problem, which is very useful in scientific applications. So now that we've discussed some of the benefits of AutoML, I think it's important to also address whether there are any negative effects of AutoML. So my usual AutoML talks, usually I just have that first slide and I move on and talk about how great AutoML is, but this talk is a little bit different. So I think in the past I've neglected to discuss whether there are any negative effects of AutoML, and I'd like to do that differently. So this talk is all about responsibility. So if we're going to talk about the positive effects, we should also talk about the negative effects. So some of the features that I listed, they can have both positive and negative consequences at the same time. So while AutoML makes machine learning more accessible to more inexperienced data scientists, and generally accessibility is a good thing, however, it also means that there could be an increase in accidental misuse of machine learning. And so by misuse, I mean things like you deploy a model to production and you might not notice that there's some kind of data drift, meaning that the data generating distribution could shift over time, which would mean the model could start to be giving bad predictions. Or maybe you just didn't realize that the training data is different from the real life test data. This could also mean deploying a model to production that you thought was a good model, but maybe you didn't actually validate that model properly, and it's actually not good. So another thing, maybe it's not robust to outliers. So there's a lot of things that can go wrong. And then lastly, since it's possible to automate the training, you could possibly decide, let's say you have 100,000 customers, you're a large company, you want to train a model for each of those customers. You now have a tool where you could, in theory, just generate 100,000 machine learning models and push them into production without really ever looking at them or investigating whether they're good or not. I mean, this is quite a powerful tool, and that would be a very risky thing to do, but I actually know that companies have done this. So it's something to think about. Okay, so let's move on to just what is H2O AutoML. So this is a function inside the H2O package, and essentially, I'll just go over like what are some of the points that we have here. So with all H2O algorithms, we have basic data preprocessing. So that could include things like imputation and automatic encoding of categorical variables. So that's just some basic stuff. But then the algorithm itself is essentially training a random search across a lot of the algorithms that we have inside of H2O. So that would include like gradient boosting machines, deep neural networks, GLMs, random forest. We also have XGBoost, which is another type of GBM. So we basically have decided, some set of hyperparameters for each of these algorithms, what the ranges we should look over, and then we do a random search. And then once we're done with that search, then we train two stacked ensembles. So one is something we call the all models ensemble. So this is basically all the models that you trained make an ensemble. And then another one is what we call the best of family ensemble, where it's a little bit more lightweight ensemble that you could put possibly into production. So if, let's say, in the first version you had like 200 models, you would have a 200 model ensemble. That's maybe not the most, you probably don't want to put a 200 model ensemble into production. So we also train this smaller lightweight one that will have the best random forest, the best GBM, etc. And then once we're done, what you get back is an AutoML object. But one of the things in the object is what we call the leaderboard, which is essentially just a data frame with all the models listed and then all the performance, the model performance, and then sorted by some default metric. And I'll talk a little bit more about the leaderboard later. And then because we're using H2O, so I haven't really given you a whole lot of background on what H2O is, but it's essentially a machine learning library in R. Well, it's actually written in Java, but we have an R API. And one of the features of H2O is that it's very easy to productionize the models. So you're able to write code in R and then get a model that's actually a Java file and deploy that into production. Okay, so this is kind of what the code looks like here. So this could be the whole script, actually. So it's only just a few lines of code. So one of the first things that you do when you have an H2O script is the first thing would be you just start the H2O cluster, and that's what the H2O.init command. And what that is it's just starting a Java process in the background, and that's where all of the machine learning happens. That's where all the data is stored. That's where all the models are stored. It's essentially a process, and that's all you really need to know about it. Then we import some data. So this is basically your read CSV, our version of it. So you import some data either from disk or from a database or S3 or HDFS. There's a lot of different ways you can import data. And so that's your training data. And then really you only have to specify 3 things in the H2O AutoML function at minimum. There's lots of other options that you can configure, but basically just tell AutoML what is your training data, what is the response column in the training data, and then how long do you want it to run for. And so you can either say the time length, so I want you to run for 10 minutes or 1 hour or 5 hours or 20 hours, or you can say the number of models instead. So if you know in advance, I would like maybe just to look at 20 models or 50 models or 100 models, you can say max models equals 20. There's some other data arguments. So if there's columns in your data, like an ID column or something that you don't want to include as one of the predictors, you can specify the X argument, and X would just be which columns from the training frame do you actually want to use as predictors. And there's a whole bunch of other things. I'm not going to go into detail, but you can look in the documentation and you'll see them all there. And then I mentioned before, one of the main things that you want to look at when you're done with the AutoML process is the leaderboard. And so next we're going to see what a leaderboard looks like. And like I said, it's essentially a data frame, and you've got in the first column model ID. And so these are just auto-generated IDs. We put the name of the algorithm in there, so it's obvious at least what type of algorithm it is. You won't be able to look at it and understand what all the hyperparameters are, but you can look inside any model and see which hyperparameters were used. And then we sort by some metric like AUC. So for binary classification, the default is that we sort by AUC. Of course, you can change that. Either you can just resort the leaderboard once it's done, or if you're really more interested in, let's say, log loss, you would specify that at the beginning, and then we actually tune the models based on that metric instead of the default. So yeah, this is what it looks like. And your leader, what we call the leader model, is the one at the top. It's generally, as long as you allow H2O AutoML to use all the algorithms. So you can turn individual algorithms on and off. You can do other things like reorder, what the sequence that they're trained in. There's lots of customization that you can do, but by default, it will train the 2 stacked ensembles, and generally the all models stacked ensemble is going to be the leader. In some cases, that's not true, but generally that's the case. So that's kind of what we get is the leaderboard. So that's just kind of an overview of the H2O algorithm. Now I'm going to talk about what is interpretable and fair AutoML. Those are 2 different things, but here's just a list of some of the interpretability packages in R. So I think I would say these are maybe the three most popular packages, at least that I'm aware of. There are lots of other ones. So IML, Daleks, and Lime. I think Lime was the oldest one in R. It's been around for a while, and the other two are more recent. And they have basically a whole bunch of different interpretability methods inside. So there's lots of things that would be considered interpretable methods, and you should just basically visit the documentation for each of these packages to see what's included. I should also note that the IML package author, Christoph Molnar, he has a really good book about interpretable machine learning, which if you just type in Chris Molnar interpretable ML into Google, you'll find it pretty quickly. It's on GitHub. And then I'll also note that the Daleks author has a keynote tomorrow, so that might be something you also might want to tune in for. So lots of these packages have integrations with existing machine learning packages in R. So you can also use H2O with these packages as well. Sometimes you have to do some customization to get it to work, but there's some links there that will show you how to use H2O with each of those packages. And then in terms of fairness, I haven't really explained what fairness is yet, but I was only able to find one package in R. There might be others, and if people out there do know of one, please get in touch and let me know. But there is one package that's called fairness, and what it does is it's a package for computing different fairness metrics. Okay, so next I'm going to give some examples of interpretability and fairness techniques. So, yeah, I just want to provide an example of what does machine learning interpretability mean. So one of my favorite interpretability tools is something very simple called a partial dependence plot, and you'll see that's on the screen, just an example of what a partial dependence plot looks like. And what it is it's showing the marginal effect that either one or two features have on the predicted outcome of a machine learning model. In this case, this is a one-dimensional partial dependence plot, but you can also do two-dimensional. Beyond that, you know, we can't really visualize in more than a few dimensions, so it's they're really just limited to one or two dimensions. So why is this useful? So one thing that you want to look for maybe in your models is whether or not particular features have a monotonic relationship with the outcome. And by that, like, why would you want to do that, or why would you care? So sometimes you know in advance the type of relationships that certain features should have with the outcome. One example would be, let's say you're building a mortgage lending model where you're trying to decide whether someone should get a high interest or low interest loan. Let's just treat it as a binary classification. So, you know, a high interest loan is not good. You don't want to be in that category. You'd rather get the low interest loan. So one of the things as sort of the designer of this system is, let's say one of your features is income. And in theory, the higher the income, like the lower the likelihood of getting the high interest loan. So we want to see kind of that relationship in the partial dependence plot. So if it's sort of all over the place or doing the opposite of what you would think, this is why it's extremely useful to look at your models after you train them. Because just because you give it that information and you expect it to learn that, you know, income should be related to the outcome in that particular way, your machine learning model might have learned something else based on the data. So, you know, that's just an obvious example, just something to look for. And then to deal with that, like if you find that you don't have that monotonic relationship, a lot of machine learning tools will allow you to force that constraint upon the machine learning tool. So you might build the model, see this you know, relationship that you're not happy with, then you can go back and rebuild the model with that forced monotonicity constraint. That's something you can do in H2O at least. And I'll get back to like more interpretability methods. I just want to give you one example. There's many methods, but this is just one. So yeah, I just want to move on to fairness. So what is fairness in machine learning or algorithmic fairness? This is a very hard question to answer. it's not one thing, it's really a broad set of problems. It's not a particular metric. So a lot of times people talk about fairness metrics, and that's really just too reductive, I think, to talk about it that way. So it's really more of a social science question. Like, you know, we can talk about metrics, we can talk about ethics, we can talk about a lot of different things. So just be aware, there's not really one definition for fairness. It's quite broad. And so why is this hard? Well, it's just, there's a lot of different things that you have to account for. So one is you have to deal with individual fairness. So how do you treat similar examples in your data similarly? And then there's group fairness. So how do you treat different subgroups of your data fairness? So subgroups could be, you know, based on gender, based on race. These are the kind of things that we look for. And then the other thing is that there are laws, at least in the US and I'm sure elsewhere as well, related to sort of encoding fairness. And the laws are quite fuzzy, let's say. It's all sort of an interpretation by the regulators, how they want to enforce that. And so there's a lot of fuzziness, and it's also a very quickly moving target. And this is a very, very active field. So it's kind of hard to keep up as to what's fair, what's not fair, what's legal, what's not legal, etc. Okay, so I'm just gonna introduce one concept. It's quite simple. It's something that's called disparate impact analysis. And it's essentially just a way to look and make sure that your model works the same on different subgroups of your population. So the very simple example is to calculate something called the adverse impact ratio. And I have a WikiHow picture here, which I thought was quite, it's just very simple and it explains it very succinctly. So I'm referencing it here. So basically this example is, let's say you have men and women. And let me just note that gender is not binary, but in the case of a lot of data sets, they have it encoded as sex, as male, female, and sometimes a third option. So let me just put that out there. And in this case, let's say we have males are accepted for, let's say, a job at a 90% rate. So what we're looking for is if females are accepted at less than 80% of that. So if we take 80% of 90, we got 72%. If that's less than 72%, then that's evidence of an adverse impact. So it's quite simple to calculate, and it's just something that's done widely in machine learning, in statistics, and even outside of these fields as well. So for classification and regression, there's different disparity metrics. So I already mentioned adverse impact ratio, also known as AIR. There's something called marginal effect. And for regression, we have something called standard mean difference. But there's a couple, I mean, there's a wide variety of metrics. These are probably just the most popular ones. And I should note that, like, there's something called the 4/5 rule, and that's why we've got the 80%. And that's basically if AIR is less than 0.8, there's evidence of discrimination. Okay, so what do you do if you do this calculation on the different subgroups of your data and you find that there is an adverse impact or a disparate impact? So one thing is you could just calculate this for a bunch of models and see if any of them are fair. And if there is one based on that metric, you could select it. But what if none of your models are fair? So there's a couple different routes that we can go then. So one would be kind of the data route, try to fix the data either by upsampling or downsampling different groups. One, we could try to fix the model. So in general, what we would do is leave out the demographic features when we train our machine learning model, but there's some approaches which would call for leaving the features in, and then you kind of regularize the impact in some way through the model itself. There's also something called adversarial debiasing, which is a new technique, which sounds kind of interesting. And then the other thing would be just fixing the predictions. So we can reweight predictions to achieve fairness. So that might be fine for general use, but maybe potentially questionable for lending, insurance, or hiring. So, if none of these approaches work, another approach is just to give up, just to not do this. Yeah. All right, so let's talk about what do we do inside of H2O AutoML. So this is all a work in progress. So this is really all stuff that we're working on as we speak. So here's kind of a list of all the things that we have on our roadmap and that we have been prototyping. So something very simple, which is you're all probably familiar with, just general feature importance. So that's sort of a global model level comparison. So if we have a bunch of models in our AutoML leaderboard, we can look at how different they rank certain features, and maybe that's useful in some way when you see that a certain feature is ranked very high and you don't want it to be, those could be red flags. There's a technique called tree shap that's related to Shapley values for tree-based models. So tree shap is the version for tree-based models. So that can be used for feature importance as well, both on a global like model level and also on a row-based level. So that's useful for something, it's very similar to the LIME method. So I mentioned the LIME package earlier in terms of what you get out. So for a particular row of data, it will tell you, how much from each feature was the contribution to the outcome. So, and that can change on a row basis. So it's interesting to look at. So I've already mentioned partial dependence plots. A similar type of thing is called ICE plots, individual conditional expectation. And then I mentioned monotonic models. So you can constrain your models. That's something that you're able to do inside of H2O AutoML. That's not in the current released version on CRAN, but we've already got that coded. So you can have constrained models, including the stacked ensemble model being constrained. So that's quite useful. I mentioned disparate impact analysis. So we're working on that. And I actually have a demo of that, which I'll go over next. And then we also compute different fairness metrics. So this is a demo. So you can actually go to this GitHub repo right now and try it out. There's an R notebook there, and it uses this data set that's called the Home Mortgage Disclosure Act data set. So this is like a law in the US that requires lending institutions that meet certain criteria to report the data about who they're lending to. And it's sort of, it's anonymized data, but you have a lot of demographic information and what, metadata about the application. So the loan amount, the term, what their debt to income ratio is, all things that could be related to whether or not you think that person could repay their loan. And so this first function that we have is called get disparate analysis. So you would give it an AutoML object, and then it will go through and on a test set compute, and the test set would have the demographic information in it, like race, sex in this case. There's one called derived sex, a column called derived race. And it will compute the metrics for all the models and look at all the different comparisons of the subgroups. So it will compare like Black women to white men, it will compare Asian men to white women, etc. It will do all the pairwise combinations and look if there's any discrimination between any of those groups. And then if that's the case, it will report that. And then for an individual model, you can also use this calculate disparate measures function to look at all the different metrics for all the different subgroups. And I'll show you a little bit more about that in a second. So here's this is a subset of the leaderboard because I couldn't fit it on my slide, but essentially it looks like the AutoML leaderboard, but we have some extra columns on there. So AIR is the adverse impact ratio, and AIR min is like it went and calculated all the different AIRs for the different groups and found the minimum, because really we're looking for, is there any discrimination in any of the groups, not just is there I mean, that's what we're concerned about. We would, the model would not be good if there was any discrimination, basically. So you don't have to prove that it's discriminatory against all the different combinations, just that at least one of them is the case. So there's a couple different metrics related to that, and then we would just have like a binary indicator column, whether or not there is an adverse impact. And so unfortunately, in this case, there's discrimination in every single model that we were able to train, and we can't use this, basically. So in an ideal world, we would have some models that did not have an adverse impact, and then you would use the leaderboard to select, what is the best model that's not discriminatory. So, it's hard to get data sets to play around with this stuff. So I'm looking for some new data sets where we can find that to be the case. But right now, what we see in this particular model, so this is the second function, which actually shows all the different combinations of sex and race, and then calculates the AIR, and then notes whether or not there's an adverse impact. And if you see, like in rows 12 through 14, we have discrimination against Black people, basically, and this is what it's showing, and we can't use this model. So this is why it's extremely important to look for this stuff. And I think one of the things that we can do is just by surfacing it within the software tools that we build, it kind of, it gives people, people might say this is too complicated. I don't know anything about this, but if we just give them the information, just like right there, it's hard to ignore. And so my goal with this is that people will start to pay attention to this, and at least even just looking at the documentation for AutoML, start to learn about these topics that they never thought about before. Okay, so we're getting, this has all been very technical, like how do we calculate fairness? This is a very technical approach to this problem. And what I want to emphasize is that this is not just a technical problem. There's actually larger things that you have to think about. And so this is maybe uncomfortable or new to some technical people that just want to focus on numbers and metrics and the math and the algorithms. So really, like when you're working with this data, it is your responsibility to kind of learn about these issues and to educate yourself and to broaden your thought process to be a bit more socially conscious, let's say. So, we are talking about people here. We're not talking about numbers in a table. This is stuff that affects people's lives and can really harm people. So Rachel Tapman, she gave a talk last week, and I grabbed one of her slides because I think one of the things, and at least there's been a lot of, let's say, discussion and controversy in the machine learning community, especially in the past few weeks, and especially since the Black Lives Matter protests and all of this stuff. People are really being forced to think about this stuff, and I think that's a good thing. So sometimes people get very technical and they want to just say, oh, this is a data problem, let's just fix the data, and they won't broaden their way of thinking about it. So I think one of the things I want to emphasize is, we can calculate all these different measures, but really sometimes we need to take a step back further and say, should we even be using machine learning at all for this particular problem? And I think there are a lot of problems where machine learning is being used where nobody's asking the question, like, is this ethical? Should we even be using machine learning for this problem? Like, let's take a step back and think about that question. So she had a nice talk last week called What I Won't Build. And she works in the natural language processing space. And there's been a lot of work, both in image classification and natural language processing related to these topics, because it's a little bit easier to see some of the discriminatory things when you build these types of systems. So my advice is don't miss the forest for the trees. Like, don't focus on, little things when you really should be looking at the broader picture. Okay, so how would you maybe, make these decisions? Your considerations can be technical using some of the methods that I said before, but they can also be ethical. And, ethics is a very squishy field and everybody has their own personal ethics. So it's hard to really talk about this in an objective way. But some of the questions that you could maybe ask yourself is, could your machine learning model, could it harm people, especially marginalized groups? And could it accelerate some of the biases and harms that already exist? That's something to think about. Another phrase that I've been hearing people in this space use quite a bit is, does it shift power? So is it, especially to the majority? I guess if it's shifting power to the minority, maybe it's not as concerning, but if you're increasing the power differential between majority and minority groups, maybe think about that. Does your data fail on outliers? Like, is that, check, see if, if you trained it all on one type of let's say you're training an image classifier on all one type of people. Let's say you only used images with white people. If you try to use it on a different population, that would be an outlier and maybe it doesn't work. Like, are you thinking about these things? Another thing is your system having strong confidence when it does get wrong answers? So these are all things to think about and to look for. And I wanted to let you know about somebody who's very prominent in this field called McGee Bru, and she is the technical co-lead of the ethical AI team at Google. She's also the co-founder of Black in AI, which is an affinity group, so kind of like Our Ladies, but Black in AI. So, so she's really she's really one of the leaders of this field and really challenging people to think beyond, like I said, beyond just like, can I compute these fairness metrics and is this fair and is this a checkbox that I have on my list here? It's really, you need to think more broadly about this. And I'm just referencing an article that she wrote in the New York Times, which you can read, and it's really kind of a social science problem, and we need to challenge ourselves to think a little bit differently about these things. Okay. So maybe just some examples. So this is just, in the last few weeks. So, so facial recognition, so that's a machine learning problem. Maybe not one that the R community deals with as much, but it's kind of an important machine learning problem, let's say. There's been like a huge industry pushback, especially since the Black Lives Matter protests, about using facial recognition. And there's even been a moratorium by like 3 big companies, IBM, Microsoft, and Amazon, saying they're not going to sell facial recognition to law enforcement. This is actually a big deal because we all know that these companies like to make money, and they make money doing this. So for them to take a stand, it's actually quite significant. And a lot of that work, or a lot of the reasons that they were able to use to justify that stance are work by people like Timnit and a woman named Joy Bulawini. Sorry, I'm totally butchering her name. She started a group called Algorithmic Justice League, ajl.org. And if you want to learn more about this kind of work, you should go there. So I would say, like, especially in law enforcement, this is a lot of where we see a lot of problematic uses of machine learning. I mean, pretty much any use of it in terms of criminal justice is really sketchy at the best and probably just totally unethical at the least. So they use it for example, predicting, for doing sentencing. So you try to predict whether or not somebody who's been accused of a crime is going to basically commit another crime. So if you think if a machine learning model can predict if they're going to commit another crime, then you would get a longer sentence, is kind of the idea. So this is like highly unethical. There's lots of stuff about trying to predict crime in general, kind of like almost science fiction, like Minority Report, like pre-crime stuff. But really what that does is just amplifies existing biases in the data. So, I mean, my personal opinion is that most law enforcement uses of machine learning are probably unethical because it's law enforcement has a long history of being discriminatory against certain groups, especially people of color. So the data's bad, like, and you can't quite fix these things with just, upsampling your data. So it's just something to think about. So, so machine learning can also be bad, even if it's completely unrelated to some ethical thing. So let's say you're trying to predict whether or not somebody has COVID from an X-ray. So there was this model that was trained, to predict whether or not you have COVID from an X-ray. And there's an ICML paper that just came out, or it's out, but it's going to be released next week. Basically, what it does is, it's very, very sure of its confidence, and so sure that when you give it a picture of a cat, it actually predicts that the cat is COVID. So hashtag COVID cat, I guess. So, medicine is another place where we're not necessarily dealing with these, difficult ethical questions. It's just more like, is this a bad model? And how do we know if it's a bad model? We need to look at it. And this is the case where, like, maybe the training data set was not rich enough, or, whatever, but, these are real models that people might use. So we have to really, really think about these things. So you can check that out at the link there. Let's see. Oops. I'm pretty sure that we already did this slide, so I'm not sure how I've got in there twice. Okay, so now that we've talked about a lot of different things and a lot of existing tools, so all of the interpretability tools that I've mentioned, some of this stuff is rather new, but these are all existing tools, and they all work with sort of our existing standard of machine learning, just normal supervised machine learning algorithms that we're all used to. So in the last few minutes, I want to just talk about some new ideas, so some new theory for rebuilding what machine learning with like a much more rich interpretable structure, sort of from the ground up. So I think if we're going to keep applying machine learning to important problems in our world, in healthcare and beyond, we really need new theory and new tools. So the current set of methods can only get us so far. So here's some ideas. So let's say traditional ML, let's say that is just what we know to be machine learning today. So it's sort of a prediction only technology. So this works well in like tech and e-commerce. Basically, these are cases where it's not high risk issues. Like if you get the wrong ad served to you, who cares? So no big deal. It's totally fine for like a lot of things like website optimization, your Amazon recommendations. Works fine when the stakes are not high. But as we've seen, like our culture, our industry is always trying to apply machine learning to new things. And I'm not sure that we can really stop people from wanting to do that. So either we have to resort to regulation, where we actually make it illegal for them to do that, or we need to have better tools that would produce more interpretable machine learning and more, richer ways of inspecting the models, let's say. So, because when machine learning fails in important ways, it can really harm and even kill people. So we should really not tolerate that. So for like a next generation machine learning system, we need to really understand more like what is the underlying stochastic phenomena. Maybe we can move beyond just a point estimation, basically is what I'm saying. So, and I don't want to gloss over many of the points that I've already made about like some things are really just we should not be using machine learning. So I don't want to just introduce a whole new set of tools in which we then blindly apply and pretend that we don't have to think about ethical things. I want to emphasize that that's not what I'm proposing here, but it's just we also need better tools. So here's kind of like a, let's say a blueprint for how can we build better machine learning. So I think here's some of the building blocks. We want automation. I think that's just, automation is nice for a lot of reasons, but it's really just sort of a logistical or practical thing. Like, we don't need to be writing the same code over and over again to figure out how to train models. I personally consider like training a good machine learning model as sort of like a solved problem in a way. Like, we have tools that do that well, and we should, make nice tools and make it easy to do. We also want to focus on exploration. So can we see if a machine learning model captured the important information in the data? Like, that's important to know. So if like in the COVID cat example, like, clearly that model did not capture like important information. It's very confused when you give it a cat picture. And so there's something kind of missing there. And the machine learning model itself was like 100% confident in its answer. So that's a bit disturbing. And then for prediction, like, could we move beyond point estimation? Could we, instead of just predict a number, could we generate the whole uncertainty distribution for that prediction? So that would be something very useful. So then attribution. So can we identify the features that are the most predictive for the response beyond like kind of just general feature importance and mean predictors? And then once we have the model, can we also check whether, I mean, some of this stuff is a little bit of what we're already trying to do, but I guess what I'm saying is let's see if we can do this at a much deeper level. So verification, check whether or not the fitted model is congruent with the observed data. So I just, I don't really, I have, 3 minutes, so I'm not gonna go into a whole lot of detail about some of the research that I've been doing with a colleague of mine, Deep. He's at Stanford, and we've been working on some of these topics. It's really more his research, and I'm trying to figure out how do we build this into in a scalable way, into H2O, into other tools. And so what we're really trying to do here is build kind of like a universal, what he's calling universal prediction machine, or UPM. So what we would do is we take our existing machine learning technology, like an XGBoost algorithm, a GBM, a GLM, all of these normal supervised learning tools that we have, and kind of add on an extra interface that will allow us to do all of these things. And I really, don't have the time to, and this wasn't the point of my talk. I kind of wanted to just generally introduce a lot of the existing stuff that's out there, and then show you that, there's lots of stuff that we can do from here, and introduce you to some of these newer concepts. There is a paper that you can get on arXiv that Deep wrote that's called Bryman's Cultures, or Two Cultures Revisited. If you're familiar, that was a famous article. I think it was 2000 or 2001 that it came out, where Leo Bryman, who's the inventor of random forest, among other things, kind of compared the statistics and machine learning communities and contrasted them together. And, as we've seen, there's been kind of like a separation of these two communities, and statisticians kind of are concerned with one set of problems, like, we like confidence intervals. We like understanding things at a more statistical level and a more, let's say, even parameterized level. And the machine learning community is more focused on, prediction, cross-validated AUC, things like that, and less about like, what is the model itself? It's more of a black box approach. So what he's trying to do here is try to bring these two cultures together. So could we have the strong, GBMs, XGBoost, that type of thing, but with more of a statistical approach, where we can not only do just, point estimation, we can get much deeper into seeing what is actually happening. And if we, basically have better tools, could we bring these two communities back together and get, kind of the best of both worlds? So, this will have to be a longer talk at another point in the future, but it's really in the same vein as a lot of the other things that I talked about today, which is how do we take more responsibility for what we're building and build better tools and frame those tools within more of an ethical framework of should we be doing all this work to begin with. So I think all of these things are really important to think about. And yeah, I'm sort of inviting you to start thinking about these things. And if you're an R package developer and you are building, especially machine learning tools, like think about like what can you do to improve your tools to have more of this stuff just readily available. And so, because we don't want to just hand things to people and hope that they're going to do the right thing, because I think we maybe have seen that that's not just going to work out so well. So let's first of all just make it easy to do the right thing, and then let's also broaden the conversation beyond just like algorithms, statistics, and numbers to include a more holistic approach to what we do. Okay, I'm going to stop there. I'm going to leave you with some resources, how to learn more about AutoML. If you want to learn just H2O in general, I would recommend the Latin R H2O tutorial that I created for Latin R 2019. And yeah, some links there. And I will leave you with my contact info here. Okay, I think I'm at time, so I'll just leave the last 10 minutes for questions.
Thank you, Erin, for that fantastic presentation on responsible automation towards interpretable and fair AutoML. And now we would like to open it up for questions from the audience. Our first question, do you have any advice for people who might need to convince their leadership that interpretability and fairness are important and that they should focus time and resources on addressing these issues in model development?
Yeah, that's a good question. So just because you personally care about these issues, it doesn't necessarily just immediately propagate to all the people around you. But I do think that you can be a source of education for either your boss or your colleagues or other people you work with. So I think just starting to have the conversations is really the first step. I think this is a long process that we're entering into. It's sort of a cultural shift, or maybe even like a, just sort of looking at ourselves and thinking, how are we contributing to negative things in the world and what can we do and feel empowered to change that? So I think if you want sort of a technical demo, if they need to see something, you can go to the demo that I referenced in the talk with the HMDA data, and you can just say, hey, here's an example of how this stuff works. It's very simple. It can be done sort of automatically. Here's a cool example of how we might do this. And then you could just try it, And if you work with data that has people data, let's say, and you collect any of these attributes like race, sex, age. I mean, there's lots of, in the US, what we call protected attributes, religion, ethnicity, sexual orientation. I don't think people usually collect that, but yeah, I would just say you can be the source of like inspiring people. There's also so many talks about this by the people that really, this is their main focus, like Timnit. I would just Google her and watch every talk. They're very, very interesting. Yeah, and there's lots of different levels of talks about this. There's TED Talks, there's highly technical talks, there's everything in between. Even if you want to introduce it to people that are not statisticians, there's a documentary that just came out called Coded Bias, which you could share with your family or friends.
Great advice. Thank you, Erin, for that. We do have another question. What do you think about the approach of using multi-objective optimization to jointly optimize fairness criteria and the actual metric of interest? and present the experimenter with the Pareto front of possible machine learning models.
Yeah, I think that's a great idea. That's one of the things I didn't really mention in the remediation slide. There are techniques where you do multi-objective optimization. So kind of some of the stuff I talked about today was not, I mean, it's not that. You're still optimizing for performance and then afterwards sorting by other things like, you know, fairness or not, but you can actually approach it as a joint optimization problem. And there's lots of literature on that. And so, you know, I think there's kind of a lack of tools in that space. So if you're looking for, you know, something to do, something to build, I think that would be, you know, new R package that could be good.
Great. Okay, and we have another question. Someone asked, could you please explain the general ideas behind adversarial debiasing?
I can't really explain it because I haven't read the paper, but I know it's very new research, I think by Google people. So I would just recommend Googling the paper and then reading it. Yeah.
An important question, actually, and another one that I'm seeing pop up. This seems really important for teaching students to build the next generation of machine learning. Do you have recommendations for new learners and their teachers?
Well, I mean, my approach is for new learners, I do think that it's important to learn the fundamentals of machine learning and learn about all the different algorithms, but I also do recommend an AutoML as a tool for newcomers because it requires this very minimal set of knowledge about what is machine learning. You basically just have to understand what is supervised learning. You know, there's a training set, there's a response. It really reduces the amount of knowledge that you have to learn to start doing machine learning. So, you know, maybe give the little demo that I created a try. I think I mean, that demo is basically a prototype for what we're building into H2O right now. It's probably going to change a little bit from that format until when we release it, but I think that could be kind of a nice introduction. And there's, yeah, an R notebook that kind of walks you through that.
Excellent. And another question, you mentioned that this is a social science issue. Do you see a role for sociologists and other social scientists who have domain expertise in structural racism and disparate impact on machine learning teams?
Yeah, absolutely. I think it's like super, super important. And I mean, the first step that we've heard people been talking about for a number of years is diversity and inclusion and stuff like that. So just even having people of like data scientists that are diverse and, you know, on your teams is important. But I think we need to go beyond that. I think we need to have people that have these skills and have studied critical race theory and feminist theory and things like that, because I mean, there's such a rich history of this stuff. And like the worst thing that we could do is just be sort of arrogant coming in with our, you know, data science, whatever degrees and thinking that we can solve what's really a social problem with tools. And I really, really want to emphasize that we shouldn't do that. I think we really need to bring in people that are experts on this, or you need to become an expert yourself and, you know, learn to be humble and really go deep on all of these topics. And it's really, you know, it's a long, you know, shift from not knowing anything about this stuff to like being really deep in it. So I think like, you know, the more books that you can read and the more videos that you can watch about this stuff, the better. So I really hope that institutions and organizations will value social scientists and pay them a salary to be involved in these projects, because I think we're going to make a lot of mistakes around this stuff, and the quicker that we get people that know what they're doing on these topics involved in the conversation, the better it's going to go. And so eventually it's going to go in that direction of having very, very diverse teams in terms of backgrounds, but the quicker you can get there, the less painful it's going to be for everybody.
All right, we've got another question. Does current training in machine learning need to change to highlight these issues? If so, what changes would you recommend?
Yeah, I think it should be important. I think, I don't know, I saw a tweet the other day that somebody said, like, learning all the ethical issues in your field should be like integrated into your learning. Like, you shouldn't have to sort these things out over many years on your own. There is kind of a history of ethics and mistakes that were made in certain fields. And if we could just know about them, we could save a lot of time. So I think, in terms of, I don't know, a lot of people learn data science stuff on their own. So there's not a whole sort of holistic structure, like a liberal arts structure to how we maybe learn things if you're doing online courses or whatever. So, what would be great is if people could maybe assemble some lists, here's a five courses into being a data scientist. Like, one of those should be an ethics course. And I think that's extremely important. And the sooner that we start learning about these things, the better.
Excellent. And that will be our last question. And this will conclude Erin's keynote. So I'd like to thank you all for attending. Thank Erin for this fantastic presentation. And that's it. I hope you enjoy the rest of the conference. Thank you, everyone.
Thank you.